very easy to print, and most of the time most of the requirement will be fulfilled with the PA. Apart from that, nylon is an industrial grade material where industrial requirements are there. So we use the nylon. Patching, as I told you, the bottle and the impact part where the impact is coming, those parts are made of the patching most of the time. And PEEK. PEEK is a biomedical material and very high performance thermoplastic. So apart from that, there are lots of metals material apart from that. We will see in next slides. But now come to the composites. Which composites material we are mixing with the matrix materials? For example, CMS is type of carbon fiber. So I hope everyone knows about the carbon fiber materials, right? Very lightweight, very high strength, very stiff material. So we are reinforcing the carbon fiber and the glass fiber. Glass fiber is also one of the composite material. Apart from that, graphene and some other composites are also there. But most of the time we are using carbon fiber and glass fiber, right? But how we use this in 3D printing? There are two different scenarios to use composite material in 3D printing. One type is continuous fiber, and second is chopped fiber. So let me do the experiment. You will see in next slide as well. And yes, and the next, let me explain a little bit about this first. So the continuous fiber, in the continuous fiber FDM 3D printing, we will use the continuous string of carbon fiber. It's a very tiny carbon fiber, continuous string. We deposit into the part and we deposit the matrix material standalone in the part. You will see image how. Let me show you. Just look at this image. This is a 3D printed part. I hope this side is also visible. So this is a 3D printed part. Inside you can see this golden color is a Kevlar, right? In the continuous fiber reinforcement, there are different more composites like carbon fiber, Kevlar, glass fiber. So this is continuous reinforcement, and the black part is a matrix material. So you can see like when I hope everyone sees the construction of a roof and a wall. So there is a bar, steel bar, and there's a concrete, right? So let me explain you in simple way. The bars can be a carbon reinforced in 3D printing, of course, and the concrete is a matrix material. In the same way, we are using the 3D printing. So it enhances the quality, enhances the strength and mechanical property in very high nanoplasticity. So this is continuous reinforcement. And the second is chopped fiber. In the chopped fiber is very easy, just like very fine parts of carbon fiber with the chopped carbon fiber that is blend with the matrix material. Like PLA, PATG, will blend and create a wire. So that is called a chopped fiber. Now, how continuous fiber printing is done? So here you can see there is a two spool. Spool is nothing, it's a material in the form of a wire, right? And the black one is carbon composite material or a composite material, you can see. So here you can see the black part is a carbon and the white part is a matrix material. That could be a PLA, PETG, anything, right? And the black one is a carbon fiber, or it could be a glass fiber, Kevlar. So this is a continuous reinforcement fiber. And if we go for the chalk fiber, so there is only one spool, which spool is only having a matrix material blended with the composites material, right? I hope everyone getting the points. Give me hand who is not getting the points and who is getting the points. Everyone is okay with that? It's not too technical, right? Okay, I hope. So here is a spool and 3D printing is happening. I will explain how 3D printing is working in the next slide. So now a little bit about the isotopic in the 3D printing. Basically, in the FDM 3D printing. For example, how it does. Let me show you this image. Yes, this is the FDM 3D printer. How 3D printing works. This is a head we call the extruder. That is get heated up to the polymer melting temperature, and this is spool. It will push the material from the very tiny nozzle, right? And it will deposit on the plate. Plate and head is moving in three axes, X, Y, and Z. As you can see second is a support material. So second support material can be used, but this is a generic example of 3D printing, how having 3D printing works. You can see in this example as well. This is a spool, dry gears, head, nozzle, build plate, and this red one is a part, material depositing. So, little bit know about how it works. Everyone seen the sugarcane machine, right? Everyone has seen the sugarcane machine. Raise your hand, everyone, right? So in the sugarcane machine, what it does with the sugarcane and the two drums. Just put the sugarcane, it will grab and it will go away. So in the same way, here's a very precise motion of the two gears, right? And between that there is a wire which is made of composites, carbon fiber, okay, and it's pushed through the nozzle where it gets heated. Now, very technical question is there: we are melting the carbon fiber? No, we are not melting the carbon fiber. We are melting the matrix material, right? Carbon fiber is in the form of chopped carbon fiber. We are not melting the carbon fibers, right? So here we are going to deposit the material, and after depositing, you will get parts like this. This is a 3D printed part, printed in PETG carbon fiber. I will give you. You can see how, right? In class. These are the composites carbon fiber parts. Okay, so this is how we print the chopped carbon fiber material, right? Okay. Okay, so this is how 3D printing works. Simple. Everyone get the point, or should I explain a little bit more if you want? You have 3D printer. Oh, very good. So I think you got the point, right? So I will move further. So what is the workflow in 3D printing? It is very important. You cannot skip the steps. So first of all is a design. But before the design, there is a requirement, right? If any one of you would like to design something, first of all you have to think about it. Or for example, if you have any problem, right? So you would like to solve that problem with some kind of a product or design. So first of all, you get an idea. For example, I have a problem in my laptop in somewhere in real life scenario. So I just thought how we can resolve this issue. For resolving that issue, maybe we require some kind of a part. So first of all, we will design. In design, the CAD software can be used. Computer design, everyone knows hopefully. And then we do slicing, right? In the slicing, what we do, for example, I have designed this bottle, right? And in slicing, what we do, we will slice this complete bottle in multiple layers. Everyone sees the bread morning, we are eating the toast and everything. There's a slices. In the same way, we will slice a CAD model in the multiple slices, as you can see here, right? And the thickness of that slice is very precise. It's come from 60 micron to 1000 micron as well, depending on the local size and depending on the other factors. But standard 200 microns. In the standard, we use a 200 micron slice. So if we slice this part multiple layers and single layer thickness is 200 micron, so we'll get a contour of particular section of that part, right? And in the setup, we will do the preparation of the 3D printer, like heating the nozzle, loading of the material, cleaning of the nozzle. These are the preparation of the 3D to do the 3D printing. Then we will do the 3D printing. In the 3D printing, we get the nozzle, plumber texture to the nozzle, depositing the thin layer onto the build plate. These layers are gradually solidified as spool, forming a final object. So let me tell you, one layer has been deposited, right? Then the build platform will go down 200 micron, 300 micron, but whatever the slice thickness. Then the second layer will deposit on the previous layer of the part, and this process will continue until the part gets manufactured. You will see that videos as well. We have a video as well. Okay, and after printing, we need to do post process, like removing of the support, sanding, painting. There are lots of different post processing after printing. Okay, now see, let me show you how depending on the cross section of that slice, and you get deposit the material, right? And the first layer has been deposited, that will go down. Then you will see after that the layer by layer process will start in this way. You can see the layer is depositing on the previous layer, and after completion the part get printed. So this is a simple example how 3D printing works. Okay, how every parts which already you have seen in your hand. So there is a support as well, right? We require support. Sometimes we require, sometimes we don't require, depending on the geometry of the part. So these are the supports. The gray part is the support, and here is the white part of the support. In 3D printing technology, supports can be removed in several different ways. For example, we can break and take it away. Why we require support? Just a simple example. When we construct a building, to construct the roof, we require a supports. Right? In the same way, we require support to overhangs of the particular geometry. And after printing, we will remove the support. We can use the supports like water soluble support and chemical dissolvable support. So we just put, if you see this part, the support is a water dissolvable. So when we put this part into the warm water, this white portion get dissolved in the water, and you will get a very delicate part. So there are different supports mechanisms, support material, right? Okay. Now come to the materials, right? This is the hot topic of this standard. So if we talk about the 3D printing material, basically on FDM 3D printing. So that start from the standard plastic. That's a non-critical applications, right? In their application, PLA, polylactic acid, and ABS comes, right? So the melting temperature of particular material is 180 degrees or 250 degrees. So when we are using this material, we have to give the result according to the material, whatever material we are using. Then we go for the engineering plastics, right? In the engineering plastic, there are lots of plastic like PP, PETG, PC, TP, TPU. TP and TPU is a flexible material, so you can bring the flexible part as well, right? The temperature is around 230 to 300 degrees Celsius. This is the melting temperature, or you can say the printing temperature of that particular material. And after that, we go for the advanced plastics. Advanced plastic used in the aerospace, chemical resistance material, and all other polymer materials. In that, P, PAN, and PN. So these are a very high temperature. It will not melt or soft up to the 150, 200 degree temperature. So where very high temperature applications are required, there we are using these kind of materials, and it's above 350 degree. As you can see, the advanced material, mechanical, thermal, chemical, high strength applications. Where these kind of applications required, we will use these kind of materials. But still, we don't introduce the composites. These all materials are normal materials, not composite materials. Now, see, understanding the composite material. Right? As you can see, there is a lots of material. These are the normal materials. Now, understanding the composite materials, how it works. Here you can see the filler material, you can see the composite material, and the key-based polymer. For example, nylon plus carbon fiber. So it will get a composite material. For example, PETG plus carbon fiber, right? PLA plus carbon fiber, PC plus carbon fiber, P plus carbon fiber. So we just introduce the carbon fiber with the matrix material, we blend it and create a composite material. What we get, what it will give the in terms of mechanical properties, extremely high stiffness and rigidity you will get when you introduce the carbon fiber material into the matrix material. You will get a high strength, dimensional stability because it will reduce the warping and desirable matte black finish. So as you can see, I hope everyone sees that part. So you will see it's a matte black finish, right? I will show you the normal part. I know this is a TQ flexible part. So this is TQ flexible part, but it doesn't have a matte finish, right? When we are using carbon fiber, you will get a very good matte finish, and the advantage of that matte finish is you will not see the layers, right? If you see this part closely, you will see like in the bright slice, you will see the slice here. In the part, you will see the slice here. But in the composite, it's little bit disappeared because of the matte finish. Okay. So now come to the second composites. That is a glass fiber, right? And in the glass fiber, again, matrix material can be any material and the glass fiber. We will see the percentage and mechanical properties as well of this material. But what will you get? You will get high strength, again, excellent toughness. So let me show you. This is a glass fiber part. It's a quite old part, so I will just give you can see. It's a glass fiber. You can see the weight. Weight is very light, right? It's a nylon glass fiber part. Okay, so you will get impact resistance, good heat resistance, and chemical resistance often is more cost effective than carbon fiber, right? Apart from glass fiber, carbon fiber is a graphene material as well, and some sort of for the just for the look and feel, metal fused materials are also available for the application. Okay, now composite material range. It is very important how you are going to add the composite materials into the polymer or matrix material and what you will get. First of all, in the continuous fiber composites, there are two types of composites, carbon composite. One, as I told you, continuous, where we are using the wire of the carbon composites, and the chalk carbon fiber. So the first, in the continuous composites, glass, carbon fiber, glass, or Kevlar, it's a continuous strands. Now, in the 3D printing part, how much we can use the carbon composite and how much we can use the matrix material. Here you can see. Typical reinforcement is 50 to 70%. You can see if you have a part and it's having a 70% of the carbon or a composite material. And apart from that, 30% is a matrix material. Can you imagine how stiff and how strong that part will be? It can replace the metal part. In many cases, in many case studies, we are successfully replace the metal part with the polymer part. And yes, the weight is reduced. There are lots of numerics apart from the weight. There are lots of factors which affect the real life application in the composite material. Now, to the short and short fiber carbon, just you can see the FDM filament as I told you. Here, the typical percentage is very less. Anyone can say why this percentage is very less as compared to the continuous carbon fiber. As you can see, 10 to 30%. Right? Composites is very less in short carbon fiber material. Like you can see, only 10 to 30%. Anyone can tell me why this volume is so less? First question from my side, guys. Anyone? No? Okay. Just give you a simple example. We are all know of the atta, right? We are making rotis. But if we add jaw atta or something else in that particular atta or flour, so if you add excess amount, you will not get what you want, right? In the same way, if we add more carbon fiber, chalk carbon fiber, the matrix material will not work properly and not suitable for FDM 3D printing because the excess amount of carbon fiber will very abrasive and it will not 3D printable ready, right? And sometimes the mechanical property also can reduce because the matrix material required for the 3D printing. Okay, and matrix material 70 to 90%. Again, the graphene fluid is same 0.5 to 10%. Okay, graphene flakes or nanoflakes, right? Yes, the matrix material is 90% to 99.5%. So these are the ranges how much material we can add into the matrix material to get a composite material suitable for the 3D printing. Already you have seen the full carbon fiber cars. Okay, Formula 1 cars, all the bodies are made of the carbon fiber. But here we are just using carbon fiber as a composites in 3D printing. Now let's see. Yeah, now come to the very important point, that is the mechanical properties, right? I hope mechanical department is much interested in that. Yes. In the continuous fiber, we use volume, right? Why? Because the complete let me show you. This image here. It is a continuous fiber. So here we can adjust the complete volume. We can adjust this width. Is this width? If we reduce this width, is the composite. So we'll assume like a volume in this particular continuous reinforcement. But we go for the chopped carbon fiber. We blend carbon fiber. So that is a weight percentage. So this is a difference. It is a volumetric and this that is the weight percentage. 30% of if we get a 100 gram of chopped carbon fiber material, 30% will be 30 grams is almost maximum 30 grams. Will be the chopped carbon fiber and that rest of the matrix material. But in the continuous reinforcement, we can change during printing because two different parts are there, continuous string and the matrix material. So we can combine different volumes. That's why I just showed the volume. Okay. Now let's go to the mechanical properties. Okay. First of all, strength. What will be impact on strength when we are using composite materials? Tensile strength will be increased by 20 to 80%, depend on the matrix material, depend on the how much composite material we are using. Okay. Fluctual strength increased by 30 to 120%. Load bearing capability improved significantly. Right? As you can see, if the strength in tensile and fluctual strength increase, load bearing capability, of course, it will increase. Right? Why? Reason: fiber, carbon fiber, glass fiber, graphene carry most of the load and restrict polymer information. Quarter point, जो most of the load है, it will bear by the composite material and the rest of the you can say matrix material will not get deformed. That's why you will get a high strength. Next is stiffness. Again, the stiffness will be increased 2 times to 6 times. Again, depend on the composites, matrix, and the percentage how much composite you are adding to the matrix material. Carbon fiber composites are much more rigid than other, better dimensional accuracy under the load. Again, you can sync with the strength as well. If you have a good strength, good stiffness, you will get a dimensional accuracy under the load. Basically, part will not get bent. Okay. Reason: fiber raise the modulus, reducing bending and flexing of the part. Part will get very stiff and strong. Okay. Weight. And in a weight, we just put here the weight as a mechanical property. Right now, in many industries, for example, UAV or drone or defense, weight is very important. Right? If your drone is very heavy, it will not get a fly and the payload will be reduced. So most of the industries in the UAV or drone, they are using carbon composite material to reduce the weight and increase the payload. Right? So how it will affect? Often lighter than the normal material. Yes, you already know that the carbon fiber is a very light material. Carbon fiber, nylon or carbon fiber plated part can reduce 10 to 20% lighter. So 10 to 20% is very huge number if you go for the UAV and drones. Okay. And the reason: carbon fiber is a low density but high in strength. In drone industry, you require very high strength but lighter parts. Right? So it will fulfill that use. Now, heat resistance. Okay, this can be applicable to the other industries where heat resistance required. Okay, UV lights are there, chemical resistance is required. So all these things will be increased using the composite. Heat deflection temperature increased by 10 to 30%. For example, PLA having a heat deflection temperature around 45 degrees to 60 degrees. But when we use a composite material like carbon fiber, it will increase. So where we are using, for example, we have an application where the temperature goes around 70 and 80. If I use a normal PLA, it will get deformed in that application. But if I use a carbon fiber PLA, it will sustain. Okay, so it will increase that. Apart from that, suitable for underload jigs, fixture, functional prototype. So I know jigs, fixture, and functional prototype, you will understand where we are using it. Reason: fiber restricts thermal expansion. Okay. and give rigidity at elevated temperature. So you will get very good heat resistance. Creep resistance. Again, the greatly improved long-term load performance and less deformation under static load. So then you will increase. Reason fiber information stabilize the polymer matrix. See here, it is also stabilize the polymer matrix. That's why we get this resistance. Now, dimensional stability and copy. Normally, I know you guys already printed the parts in FDM. If you try to print ABS, have you tried ABS? Printing, sir, you? Okay, I think you have already printed PL or PET. But if you tried ABS will get warped from your physical printer. Very easy. Because it's required a chamber temperature. Right? But what if we add carbon composites in different matrix material, it will reduce the warping and shrinkage. PLA having a very high tendency of shrinkage, right? So that's why it get warped from the back build plate. But if we add carbon composite or composite material, it will reduce warping and shrinkage. Better tolerance will improve. You will get good tolerance rather than the normal material. To smoother hovering and cleaner corners. Because it's kind of sharp turns. Reason fiber limits polymer contraction during cooling. Okay, if you cool ABS or nylon or PP polypropylene, cooled very fast, right? So it will get shrink and get off on the bed. So it also reduces that mechanical property and increase the printing of the material. That's why sometimes we say if not if the particular material is not get printed, get a carbon composite version of that particular material. It will get settled on the bed. Okay. Next, surface finish. Surface finish and ablative. Composite of more matte texture finish, as already you have seen, can be slightly rough due to the fiber. So, already if you see this part, you can pass through. You can feel this surface finish is much gooder than the carbon fiber and the composite material like glass fiber. Can be slightly rough due to fiber, much more abrasive. See, if the material is abrasive, you need a nozzle. You have already seen there is a nozzle, which is material is coming out of it. If that is a brass nozzle and the material is very abrasive, the nozzle will get stopped. That's why we use a harder nozzle required for the composite material. Next, impact strength. Composite effect varies. Glass fiber increase impact toughness. Glass fiber. Carbon fiber sometimes decrease impact strength more brittle. So it is depend on your application. Again, what kind of application you have, according to that you have to select the particular material and the composite material as well. Graphene improve impact strength at low loading. Right? So depend on your application, you can select what kind of composite material you are going to use. So this is kind of a summary of the mechanical property. What kind of mechanical property affect by different type of polymers and composites. So if you take a property strength, if you print it with a normal polymer, like only PETG, only PLA, you will get low to medium. But if you use composite, you will get a high, major improvement will be there. Right? In the same way, stiffness low, composite, you can use very high, 2 to 6 times, heat resistant, medium to the high. Better thermal performance your part will be. Weight again, lighter part will get. Warping, higher stability will get during the printing. Right? Fatigue, it will be high, less crack and core. Impact strength depends on the fiber type. As I told you, impact strength is dependent on the fiber type. What kind of fiber you are using? Abrasion, nozzle will get wear in the 3D printing method. Okay. Now move to the next. What kind of factor that influence the composite materials? As I already told you, fiber content. So higher fiber content, you will get a higher strength. Stiffness, too high cause brittleness and poor flow. Now, let me tell you, if I give more than 30% carbon composite in the matrix material, you will get very high strength, but it will cause brittleness and poor flow in the liquidity. That's why the limit is around 30%. It is a maximum limit to add a composite material. In again, the type of fiber is also important. Type fiber type like carbon fiber, glass fiber, graphene. These are carbon fiber, higher stiffness you will get. Glass fiber, higher impact strength you will get. Graphene, conductivity and mortality. Okay, fiber length is also important. Fiber length and aspect is also important. Long fiber, higher strength. Yes, absolutely, absolutely. Much higher than the chalk carbon fiber. And it's yes, there's a orientation is very important. For example, if I'm going to just let me take you example. Just consider this is not a pen, it's a shaft, right? It's a shaft where we are going to put in some applications. If I am going to print in this orientation, the layer will be in this direction, right? Or and I will put the shaft into the shear force. So because there is a layer, it will break very easily. Because in the z direction there is a low strength. But if I print in this orientation and I will lay down continuous fiber in the same orientation, the strength will be much higher in this orientation. It will give you more applicable parts. That's why the fiber orientation is also very important in what orientation. But this is on continuous fiber. In chalk fiber, you cannot decide in the fiber orientation. Okay, so apart from that, matrix material is also very important. You cannot, for example, peak, and let's take example of PLA. PLA is very low material, peak is a very high material. Let me tell you the cost. PLA you will get around most of the most 1,000 rupees per kg. Good material. In carbon composite you will get 2,000 rupees per kg. But if you go for the peak, you will amaze that the 250 gram material will cost you around 35,000 normal. But it's the carbon composite again 45,000 for the 250 gram material. That is why the material is very important. Okay, matrix material. Fiber matrix bonding is also very important that influence that factor. Like strong bond, low transfer will be high. Weak bond will stay delamination. In basically, apart from these factors, there are some other factors depending on the 3D printing. Right? These are the materials, and the next is the 3D printing. Which factors affect the as in the 3D? One is layer height. Layer height is nothing, it is the height of that particular slice part. As I told you, the slice is the multiple slice. See, lower height, layer bonding will increase, Z strength will increase, right? A height, if the height is low, the strength will be decreased and the time will be also decreased. Let me tell you simple in this slide. Let's assume this part, if I slice at 200 micron and I will get 100 slice, right? If I slice at 100 micron, the same height, how many slices will I get? 200, double. So the bonding will be double. If the bonding is double, definitely strength will be increased. So this is simple thing. Apart from that, the printing temperature. At what printing temperature you are printing? Higher temperature, you will get good bond between the matrix material. If the temperature is low, you will not get a good bond between the matrix material. Because here, the bonding is between the matrix material, not the composites. In printing, because chalk carbon fiber is the form of a very fine chalk. Yes, that's right. Okay, so nozzle depth is also important. Ensure fiber wet out. So the fiber need to be wet out as well. If the matrix material is not wet out, sorry, the fiber material is not wet out with the matrix material, it will not get good bond. So that why temperature is very important. Low temperature, poor bonding. Simple as that. Bad temperature is also important, reducing warping, improves dimensional stability and adhesion. There is a grid platform which need to be heated, so it is also important and affect the composite 3D printing. Printing speed, it is very important in composite 3D printing. If you print very high in a speed, you will get a low bonding. If you print low, you will get a high bending, high strength, but the time will be increased. Let me tell you about the time as well. For example, 100 layers will get 2 hours of printing. 200 layers will reduce walking. For example, I am printing some kind of a flat part like this on the bed. Okay, this is the bed. So bed needs to be heated. If the bed temperature is low, basically we put the bed temperature as HDD or PG of that particular temperature. If the temperature is low, it will start that walking like this part from the bed during printing, and it's get started the part that failed. So this will reduce the hopping and improve the dimensional stability. So bed temperature is also important in printing. Okay. Up to that, we just discuss about the average printing. Okay. So in between, I just want to know if anyone has a question up to that, then I will move further. Any questions from you? Yes. Yes. Yes, it will reduce the biodiversity if you use the carbon fiber. Yes, definitely. Yes, yes. Yes. See, there are lots of different ways to use that support. One of that is you can get a filament manufacturing machine. You just shred that material and you will get a, again you will get a material. Because we are using here polymers, right? So polymers get be reused by melting and yes, but it will at least 3 to 4 times be used. We are using it, many guys are using recyclable materials. And you will get many brands are using the recyclable polymers. So this is the one of the example. And apart from that, technology is evolving very fast in 3D printing as well. You can use that support material for different composites as well. For example, if you are printing PLA with the carbon composites, and PLA is a different like a made of a support. So you can use that support and again create a composite material out of that material by adding the composites. Apart from that, if you talk about the slicing, there are different technologies or slices available in composite printing or dual color printing. The wastage material will push into the support material, right? So it will not get wasted. For example, if you see bamboo lab printer, it's give you lots of wastage, right? But if you set your slicer in very good way, that waste material, if the part enters support, that waste material will lose as a support, and that support we can also reuse. So, not yes. Yes, I got it right. You want to add glass fiber, carbon fiber to the matrix material. Up to that, I don't have that knowledge that I don't see any kind of material yet that is having a carbon fiber and glass fiber as well. Because there is a challenge. Glass fiber and carbon fiber will, if we mix together with the matrix material, yes, because bonding is also required with the matrix material. Maybe they are not that bond. Compatibility can become, but yes, but we can have a we can try. Uh, yes, yes, you can print, but see, there's a lots of parameters, limited parameters for printing. As I told you, if you add more than 30%, the material will more abrasive and more brittle. It will not stable for printing, right? For example, I just don't have. Yes, I have. These parts are made out of ceramics, right? You can see I will keep the part as well. So this is a aluminum and zirconia. The raw material, the filament, the wire of this material something known as penalty. So still we are able to break, but in carbon fiber there is no aggressiveness. But in carbon composite there is lots of aggressiveness. Right? We need to use a Rubik nozzles, harder nozzle, and it will get distorted in multiple ways. So there are lots of yeah, I make the part back thing, so just I will show you how ceramic printing as well. Okay, anything else? Yes.
Sir, we are, if you look into the bicycle market, the more of the high-end bicycles are from carbon fiber frame. They are producing carbon fiber frame and they are very costly bicycles. Every part is carbon fiber because of the reduced weight. Why they are not shifting because of the increased advantage of 3D printing? Why are the companies not shifting towards the 3D printed bicycles? Because of this, you have mentioned the composites, carbon fiber composites. They are offering greater, properties. So why they are not moving towards that part? Because the carbon making carbon fiber bicycles are very, cumbersome process.
So let me give you a simple example of that. You heard about the Formula One car. Is there any cost limit for manufacturing that car? There is no cost limit. The car is very very expensive, Formula cars. But in terms of cycles, the cost is very important. Or bicycles, the cost is very important. So one of the factors is cost. And the second is right now what are technologies we have available. In the carbon fiber, if you make a cycle, you need a kind of a rod, right? And rods can be manufactured in much more easier way than the 3D printing. And full carbon fiber, not without matrix printing, like rods, sheets, plates are available in the carbon composite. Even there is a sandwich as well, carbon fiber, Kevlar, and resin. They are using resin to create rods and that. So with that will be more cost effective than the 3D printing. 3D printing basically fits most of the time where the traditional manufacturing is not able to perform. Right? Some kind of a you can say the some parts are not able to manufacture with the conventional manufacturing method. Here 3D printing will comes. So one of the factories cost from my point of view, they are not using it. But yes, I think one of the companies, some of the companies are using this technology for creating the levers and all those things. I will show you a lever example as well. I think I should have a photo of that. They are replaced the bike handle of the metal bike handle with the carbon fiber, and that is almost a higher than the aluminum strength by using the continuous reinforcement under the lever. So I will show you that. Okay. Any okay, sir? Okay. Any further questions? Okay. So now, apart from FDM, what are the top 6 non-FDM printing technologies which is utilizing the composite materials? Right? Up to that, we have just discussed about the FDM, fused deposition modeling, and all this. First of all is SLA, selective laser sintering. So in this technology, let me show you about the technology first. So let me show you how different technologies are work. So if we classify the 3D printing technology depend on the material. So we can classify under these three raw material types: solid, liquid, and powder. Now it's about the technology. Okay. So if we talk about the solid, fused deposition modeling, as we have already discussed, this technology will under this classification. Allo and magnetic object manufacturing. It is another technology using which we are using the 3D printing. In the liquid, SLA, DLP, polyjet, these are the technologies. In powder, we are using SLS, MGF, and SAF. Right? So these are the different technologies which can be used depend on the powder. Now see little bit principle how this technologies work. For example, SLA. Okay. In the SLA, you can read or I should read this. You read? If you read, then I will explain. Okay. Okay. So let me explain. This is a typical example of a SLA printer. This is a build plate. Okay. This is a part, and the small ribs are the subgroups. Okay. This is a build platform, and here is a resin layer tank. This is a resin tank. again the layer will get solidified, up layer will get solidified, and in this manner the complete part will be manufactured in SLA technology. But in different technology, different type of post processing are required. In SLA, we need to cure the part because it is a liquid based printing. So yes, it gets solidified, but again we require a UV treatment to get a more solidification of the part. So this is the SLA technology. Next is DLP. DLP is same technology, but this is slightly different. We cannot say the slightly different. It's a good difference. The technology is simple, but there is no laser. There is a lamp and a monochromatic display, which create a shape in black and white. And there is a reflector, there is a lamp, UV lamp, which will throw the light on that particular transparent display. Which portion is black? That whatever the portion is black, light will block. Whatever the portion is transparent, light will pass. And in the one complete layer will get solidified. The major difference is laser and the lamp. So this is much faster than the laser because it just brings the light for a few seconds. The complete layer can be solidified. In the laser need to trace the complete geometry. So this is something kind of same. Laser is used here. Next is polyjet. It is very expensive technology. You will amaze how good quality parts will produce. So in the MJF, there is a head and UV lamp and there is a nozzle. Nozzles are same something like a paper printer. Just for the example, and just assume you have printed. Let's example these are the 50 papers, right? So the 50 layers. Let's take example of 1000 layers. So it will get up to this size. Approximately, just take example. So single paper printing, as you can see, is printing. So take example, this printing is printing as a layer in the same paper manner, and again, second layer will be sprayed and printing on the previous layer, and this process will continue. So this technology called polyjet, it is very high-end technology, which use multiple colors. You can easily print parts same like a production part. You will amaze me how much good quality you get. Here there is a different nozzles and it will create a RGB color as well. So full color printing can be done with this technology. Okay, as you can see, you will have printed head model. This is a support build platform. Yeah, build platform will go down as per the nozzle, as per the layer height. And this is polyjet technology. Next is SMS, selective laser sinting. Here you can see two buckets, right? And this here is a part. So what is happening? Initially, this will be down and this will be almost up. So there is a roller which will roll the powder on the build platform, and the laser will be there which sinter the powder, right? And the bed will go down in the same manner. Bed will go up, roller will come, it will deposit the next layer of the powder. The laser will sinter it, and this will be continued until the part get manufactured. It is a powder-based technology. Okay, and the next is MJF. It is also powder-based technology, but it is a combination of polyjet as well. So here we are using powder and we are using agents, fusing agent and detailing agents. Here we are using the ink for spraying. Here we are using the agents. Agents are kind of a resin. Here you can see. So again the powder will deposit. Here you can see the two. Build type of powder. Somewhere is a bucket. Second platform is there. So the powder will get deposit. The agent will be sprayed, right? Not tracing. Here we are not using the laser. This agent will be sprayed. Then UV lamp will come and UV light will solidify that detailing and binding it. And the part will get manufactured in the same way. Here. Yeah, the FDM we have already seen. This is FDM. So these are the several several 3D printing technology. Apart from that, there are lots of technologies available. But I just showed these technologies because these are the normally available technologies which are in the market. Okay, now let's move to our previous presentation. Okay. Okay, so SLS, as I told you, SLA, DFE, material jetting, binder jetting, DD is a direct energy deposition mostly used in the metal printing. Okay, so these are the technology. Let's see how composite and what are the composite are we using in the industries. So first of all, selective laser sintering. Here we are using the polymer composites. Use composites powder such as nylon 12 plus CF. Right? In the FD we are using the blended form of a wire. Here we are using the powder. The technology is the same. Sintering and layer by layer process. Nylon glass fiber, mineral filled nylon using TPU composites. For example, you require a flexible part, so we can add a TPU composite. TPU materials are composite with nylon or different type of materials to get a flexible part. So what you will get a good and great for strong performance functional parts with excellent heat resistance. Again, see, the mechanical properties will be enhanced in the same as in the FDM. But how this technology is using, I just illustrate here. Okay. The second is SLA DL2 LPC composite polymer resin. Here in the resin, there is a liquid. In the resin, they are using ceramic filled or carbon filled and graphene loaded resins. Again, the composite powder is mixed with the resin and it gets solidified and technology is the same. The next is material jetting. Nanocomposite resins are using material jetting. There is a detailing agent and the binding agent. In that agent, we are can be used a nanocomposite material to enhance the mechanical property and other properties of the material. UV curable droplets mixed with the nanoceramics. UV curable droplets mixed with the nanoceramics material, right? Toughness, you will get a tougher polymer, elastomer blends. Also can be used very high resolution multi-material composite printing. This is another technology where we are using the multi-material printing. Apart from the polyjet is also using for the multi-material printing. So the next is binder jetting and metal ceramic composites. Use powder for MMC metal matrix composites. CMC stand for sand polymer composites. Yes, sand also can be used. Final part sintered high strength composite structure. In this, the sintering is also required. I will show you in ceramic and metal how sintering is done and how dewelding is done in the upcoming slides. DED direct energy deposition, metal matrix composites are used. Right now, this technology is evolving very fast. We have developed all metal 3D printer in Indore, which is based on the DED. Okay. So deposit metal powder plus ceramic and graphite reinforcement. Here is again the composites ceramic and graphite. For example, titanium plus ceramic, aluminum silicon carbide, inconel composites. So they are using the powder matrix material as a powder, and composites can be used in kind of this material. Used in aerospace and liquid industries. Right? And the robotic composites use prefix tapes, chalk fiber thermoplastic companies, aero, orbital, impossible objects can be made. Print large continuous fiber reinforcement structure, non-additive robotic printing. In robotic printing, basically it's a robotic printing where we are using the robot. In that scenario, where also can be used the composite material. So these are the summary basically. It's not a very explainable thing because the session will be more long and more boring. Okay, so now composites range. We have seen the FDM. There is a range of a composite material. There is a range of a different other technology on the composite material. For SLS, 15 to 40%. 15 to 40% of fiber, filled glass or carbon fiber can be used in the powder. Again, if we use the excessive amount, maybe the it not able to printable. Mechanical property will again increase 20 to 60% mechanical property and strength you will get. In SLA and DLP, you will get 5 to 25% salary. We have a printer at our office in Noida, P3 for the status that is the salary part, salary printing. So there's a slurry. You can assume it is a liquid and in that is a salary powder. So it's giving you a very good and high function that salary. So again, the mechanical strength is given by 10 to 40%, stiffness and other resistance. Basically, all mechanical property will be enhanced, right? Where you require an enhanced part than the normal polymer, you have to use the composite material. And there's a very big boom in the composite material. Right now, the composite in the previous years, or if you take example 10 years back, composite composite materials are very less available in the market. But right now you get a high amount of composite material and different composite material you get like glass fiber, carbon fiber available very easily, and that can be printed in your FDM 3D metal normally like under here or okay. Layer liquid additive manufacturing silicon composite 5 to 10%, again 10 to 35% improvement in tear, strength and elongation control. Right, FFF, it's a continuous base basically. For 30 to 60%, 100%, 600%. See, here the 600% is high because we are able to replace the metal parts by using the continuous carbon fiber. Okay, and DLP ceramic composite like 40 to 70% ceramic loading alumina, GDS, nickel carbide as a composite in this particular technology. Okay, so this is the simple composite range. Now come to the you would like to get a little bit break for 5 to 10 minutes. I want. Just take a 5 minutes break, then we will continue the next one. You will get good examples and videos as well. So just
थोड़ी सी लेट हो गई तेरे जैसे दोस्तों को लेट पहले तो रजिस्ट्रेशन तेरे को जो सर्टिफिकेट मिलेगा उसकी वैल्यू भी यही है और जो मेरे को मिलेगा उसकी वैल्यू इसके सर्टिफिकेट